Any questions before we start? I'm just pointing out something on Moodle. Early module feedback on Moodle. If you're interested in providing some feedback on how you think the module is going. It's very early, isn't it? Yeah. Like we just started. But anyways, you can leave some feedback like, I think everyone should automatically get 100% of the module. Or I think I should get 100% and everybody else should get something lower. Okay, we're going to talk about so-called quantitative methods, quantitative research methods. Question?
Yeah, I have a question. It's not showing up.
Early module feedback's not showing up?
It's not showing up.
Maybe I need to, early module feedback. Nobody can see that, yeah?
It's not.
Maybe I need to do something there. Hold on. Gesundheit. Okay, maybe it works now. Maybe you can see it now. Refresh. Still no. Okay, don't worry about it for today. It's still too early anyway. It shouldn't work. Why should it work? Okay, so we're going to talk about quantitative research methods. This is essentially like introduction to statistics. This is everybody's favorite subject. This is only a very tertiary introduction to the topic. Usually you take a whole module just on this topic. So there's not that much we're going to say in this one lecture. It's just an introduction to this topic, basically. So statistics are always connected to the evaluation of some research. You have a hypothesis, you have an idea, you want to demonstrate that your idea works or your hypothesis is true or your hypothesis is false, and then you need to provide evidence. Like, how can I convince the rest of the world that what I'm saying is true, right? So you're trying to build evidence for your case, and statistical methods are one way to provide evidence. They're not the only way, but they're one way. And what often happens is that you evaluate whatever the work you're doing compared to someone else's work that has done something previous that's similar. So, for example, you're trying to build something that's quicker than a previously published paper. Or is it more accurate? Maybe you're trying to demonstrate that your method is more accurate than previous work. Or maybe it solves new problems that weren't solved previously. Or maybe it scales better, right? As the data set sizes increase, maybe your solution scales with data set sizes. But in all of those assumptions, there's a comparison taking place, right? You're comparing your work with somebody else's work. Sometimes we can make a comparison theoretically, right? Just based on mathematical proofs. And for some projects, the results will be statistical, right? You'll say, I've run my algorithm 10 times, and on average, it performs twice as fast. On average. So average is a statistical measure, right? So you're making a comparison using statistics. So quantitative data can be expressed using quantities or numerical data, right? This is quantitative research, right? Based on numbers, right? Those numbers could also be expressed into categories, like strongly disagree, agree, strongly agree, right? Those are different categories, or like and dislike. So it's not always just a single number, like an average, for example. And we have lots of different kinds of data, right? Everybody's familiar with that. We have numerical data like temperatures, times, distances, salaries, and so on. We also have categorical data, right, that we just talked about, like hot, moderate, cold, or type of operating system, color, type of color, country. We have ordinal data, for example, like a letter grade on an exam, extreme dislike, neutral, like, extreme likes, and so on. So that's called ordinal data. Those are categories that can be ordered, right, that have a specified order. And sometimes these are objective quantities. Numerical data is usually thought of as being more objective as opposed to subjective. And sometimes we have subjective quantities, like how confident do you feel about something? How confident are you that you're correct? Or did you like this method better than the previous one? Or did you dislike this method compared to the previous one? So that's more subjective. And so we're trying to provide evidence that what we're doing is correct or useful, and we're trying to do it in a quantitative way, and statistics are part of the tool set, right? If we gather quantities or a set of data, we get a data set, and then we generate statistics based on the data set that we have derived, right? If we run an algorithm 10 times, we get 10 performance times. We can look at how much memory is used 10 times, right? Or we can run a process. Imagine we run a process that takes 60 seconds, right? We can measure the performance at 10-second intervals, right? And then we have a data set, right? And we can use statistics to try to say something or infer something about the data set, right? Here's an example. Are houses affordable in this given town, right? In that case, we would have to look at the house prices of hundreds or thousands of houses and then make some comparisons. And we might use statistics. For example, most people in the town can borrow around $120,000, so maybe that town is affordable, depending on the average house price, for example, right? Everybody with me so far? I'm going through the elementary stuff a little bit fast because I think you're already familiar with what I'm saying and talking about. This is something you might not be familiar with. Probably you're seeing this for the first time. It's called the Datasaurus Dozen. So statistics are very useful, generally speaking, because they provide some description or summary of a data set, right? They essentially summarize a data set in a concise way. But statistics alone are not always adequate, let's say. And this is an example. This is called the Datasaurus data set. It looks like a dinosaur, right? That's a set of points. And if you trace the outline of those points, it looks like a dinosaur, right? And if you can compute some statistics on those points, right? You can compute a mean value along the x-axis. You can compute a y average along the y-axis. You can compute the standard deviation along the x-axis. You can compute the standard deviation along the y-axis. And you can compute, for example, a correlation coefficient, and you get results that look like this: 54, 47, 18, 26, and minus 0.06. Right? And that's for the data. That's for the Dinosaurus or the Datasaurus in this case. But guess what? If you run the same statistics on these other dozen data sets, you get the same results, the same statistics. So you get the same y mean, the same x mean, the same x standard deviation, the same y standard deviation, and the same correlation coefficient. But the data sets look very different, don't they? So statistics are very useful, but they're not the whole story. They're useful, but it's also good to visualize the data, obviously. And there's more information on this if you're interested. This is interesting, by the way. That's why it's in this slide. So you're encouraged to look at it in more detail outside the lecture. And statistics are usually descriptive, right? They're trying to provide a summary of what you're seeing, or a summary of a data set. So using measures of average and distribution to summarize different data sets and then compare them. So these are often used to make comparisons between data sets, right? We can also use visualization like in the previous slide, so we can see the data that we're generating the statistics about. And then inferential statistics are based on sampling, right? If you have 7 billion people in the world, it's hard to measure to measure everybody's height, for example, and then take the average height of 7 billion people. So what you do is you take a sample of the population, maybe 1,000 or 10,000, then measure the average height and hope that it's a good reflection of the rest of the population. That's called inferential statistics. So if we want to make some inferences about a data set, there are two very common ways we can do that. We can measure an average. These are characteristics that are the most typical to look at inside of a data set. Or a central tendency. What does the average or what does the middle look like? And what does the distribution look like? How varied is the data? Right, so we want to be able to have an idea of what the middle looks like and what the variance from the middle looks like. These are the kind of standard approaches in terms of quantitative methods and statistics. So one of the ways of computing the average is the mean, right? Adding together the values and dividing by the length. I think this is something that everybody's familiar with. This is computing the mean in Python. So adding the values together and dividing by the length. This is just one way of computing an average. And averages are very, very useful, very, very common. There is sort of one drawback with averages in that sometimes the average can get thrown off by an extreme or outlier value. So if a group of students, let's say, earns 10 pounds an hour, but there's one special student that earns £1 million an hour, then the average will get thrown off. It will no longer represent be a very good representation of the sample or the students. One way to alleviate that is to use something called the geometric mean, the square root of the product of numbers, when you're trying to find a meaningful average. Another representation of the middle of a data set is the median, which is related to the average but not the same. It's the middle value after you sort the values. So you sort all the values and then you take the middle one. And that's the median. And that's probably a better representation of the central tendency of a data set than just the mean. It depends on the distribution, right? So this is not going to be distorted by a small number of outlier values, right? Everybody with me so far? Yeah.
Why the geometric mean?
So the geometric mean is the square root of the product of numbers. So it takes out the, whenever you square two numbers, it takes out the negative. So imagine you have a negative value. When you take the square, then it eliminates the negative value, puts everything on the positive scale, and it tends to reduce the variance. That's the tendency, to reduce the variance.
The large number is still
Yeah, and then we take the square root. We take the square root. And then the variance is reduced. Yes. This is a good question, by the way. I think what I would really recommend, I can sit here and use my hands and my words, but to really answer this question, I need to go deeper and use illustrations and things like that. I've put in some of the slides some YouTube videos, some YouTube channels, to statistics channels, and they use illustrations and go into more detail. By the way, I'm watching these videos too. So slides are okay, but if you have somebody with a whiteboard and making illustrations and drawing out the concepts, it's better. So that's why I put in some links to YouTube channels that go to that length. Okay, and I didn't go into depth on the averages because I think everybody has a good sense of averages already. By the way, these little screenshots are Python, using Python to compute these statistics. Does anybody know what else we can use to compute all these numbers, these statistics?
R.
R, yep, that's correct. Anything else? MATLAB, yes, correct. Okay, this audience is awake. Anything else? Excel, yeah. So you can find YouTube videos of computing all these videos in R, Excel, what else do we Python, MATLAB. You can find YouTube videos of all of these things. And I watched one just the other day, just on Monday, computing the so-called Ttest using Excel. We're coming up to the Ttest. So it's all within your grasp, right? So mode is another kind of average. It's just counting up the value that appears the most often. Right? If you have a data set with values, sometimes there's a value that appears the most often, and that can be the mode. Right? And that's particularly useful for categorical data. Right? Like, what is the best-selling product? What is the most popular political party? Right? Mode works on this non-numerical data. Right? It's a kind of, what's the most popular value in this data set? Okay, so the averages are very useful, right? Because they summarize, you can have an arbitrarily large data set and you can compute the average and you get kind of a summary of that data set in one number. So you're reducing the complexity, right? And that's a good thing. But sometimes you might lose some information. So here are some things to think about. What does it mean to have an average crime rate, right? Imagine we have something like the average number of crimes per square kilometer in a city, right? So it's something to think about, like trying to interpret what an average crime rate is subject to is a little bit, has some subjective interpretations. An average might indicate a characteristic of a majority group, but it might also be more interesting to subdivide the population or the data set into subgroups and investigate the subgroups individually. Like, what is, an obvious example is, what is the crime rate between males of a subgroup and females, right? It's going to produce different averages. Of course, the women commit a lot more crime. I'm just kidding. But it's going to produce different averages, right? So we can break things down into subgroups to get more averages, right? And if you keep recursing, then you actually get down to individual people. So there's a balance, right, to be struck there. So those previous slides were all about the sort of central tendency of a data set, like how to try to summarize the middle or the average. And the next slides are about this distribution property. Like how is the data distributed over space or time, for example, over X and Y. And in the Datasaurus Dozen, you could see that they all had different distributions, right? With the same statistics. So distribution is associated with variability. How much variance does the data set exhibit? So these three data sets all have the same average, but they look different, right? Their variability is different and their distribution is different. One is very narrow, one looks like a so-called Gaussian distribution, and then one is another spread out, so-called, looking kind of like a normal distribution. And we often use this phrase, normal distribution. Has anybody heard that phrase before? That means there's one kind of hill in the data. It's like just one peak, let's say, as opposed to two peaks or three peaks. You could have two hills in a data set, or two kinds of averages. That's called a binomial distribution. This is a so-called normal distribution. Standard deviation is another is the standard way to describe the variability or the distribution of the data, a measure of how varied the data is. That's the standard deviation. So for normally distributed data that is in this shape of a hill, around 68% of the data are within one standard deviation. So this dark blue region represents one standard deviation, or around 68% of the data. So if we add this 34% plus 34%, we get 68%. This is one standard deviation. And this tells us, this is a measure of the variability of the data. Right, the bigger that number is, if you can imagine, so in this data set it's 21. If you can imagine this being, say, instead of 21, 42, then the hill would spread out. It would spread out to like double the width and the variability. If the standard deviation shrunk down to 10, then the whole thing would get very narrow. And then two standard deviations. This is the region of two standard deviations. So 1, 2, right? And that represents about 95% of the data. This is the kind of standard statistical measure of variability or variation. So one of the things that one of the curveballs of measuring standard deviation is if the data is not normally distributed. In other words, it doesn't have a nice hill shape with just one peak. If it has two hills with two peaks, then we might lose some of that information if we only look at the average, for example, or the standard deviation. This is an example of a data set with two peaks, right? Here's one hill and here's another hill. This happens in our software engineering class, by the way. We teach a software engineering class, and the scores look more like this than the single distribution sometimes, right? That's also called multimodal data, or multiple peaks in the distribution. So it's always good to see the data, right, to visualize it. We're going to talk about that next week, by the way, some visualization. So there is variability, right? We could be measuring standard deviations, right? Now, we could, then what happens in the next step is, imagine we have two data sets, and we want to compare the variability of both of those data sets to each other, right? That's what often happens. This is what we're leading up to. So usually when you run an experiment, you collect a bunch of data, and then you want to compare your data set with somebody else's data set. And the statistics are the one way to do that. That's what we're leading up to. So first we start with our own data set. We learn how to generate statistics like averages and deviations and variations. And now we want to compare those to somebody else's data set. That's where this is going. So maybe we want to measure one feature, but there are multiple factors involved. So imagine an animal's data set. We might want to measure the height between multiple species, right? Maybe we want to compare the opinions of two different groups of people, right? That's another possibility. And maybe we want to compare, for example, the effectiveness of a drug on two different cohorts of people. That's very common, right? So how can we do that? What does that entail? We could use statistical methods to see whether there are differences or how two groups compare or two data sets compare to each other. This is the most common thing. For example, do penguins of different species have different average heights? Are mathematics students happier on average than computer science students? Does one drug work better than another drug on the same group of people or similar groups of people? Right? These are all examples of where we would want to use these statistics to try to compare two data sets. And then the data sets, when we make comparisons between data sets, there's always some differences, right? The data sets are never exactly the same, right? So if I draw the conclusion, for example, I measured a bunch of penguins and I got a height of 450 millimeters, and a different one that was 350 millimeters from a previous experiments, can I draw any conclusions based on those measurements, and can I try to quantify the probability that my conclusions are correct or accurate? If 61% of students are happy with their course and only 60% of computer science students are happy, can I really draw conclusions from that? Is there a way that I can support my conclusions with statistical evidence? Are those meaningful differences? or not. So in both cases, there is a difference, but is the difference significant or robust or however you want to call it? Can we say how confident we are that those things are different and in a meaningful way? This is also called inferential statistics. So probably everybody has heard of this term, statistical significance. This is very, very popular, right? You might get a result that says my algorithm is faster than a previous algorithm, or these heights on average are greater than these heights, and somebody will say, but is your result statistically significant? Has anybody heard that before? Very, very common. So that's what we're going to talk about now, is statistical significance. And what it's trying to measure is whether or not it's trying to measure confidence in our results. So we have two data sets. We've measured some differences between the data sets, and now we're trying to assess whether that difference is how confident we are that those differences are meaningful or just an accident. It could happen that it's just an accident. That, you know, if I divide this class in half and I take average heights and the two averages are the same, it could be just an accident, something like that. This is about robustness. That's another word you could use, or the reliability of your conclusion, or the confidence of your conclusion. How confident are you that what you've derived is correct? But not about how much the difference is. So you can have small differences and be very confident that you're correct. Right? But you can also have great differences, and it could just be by accident. So we're talking about how confident we are in our assessment, in our derivatives, in our conclusions. So in most cases, there is some overlap between these measures, but we need some statistics to measure the robustness of the difference. This is the so-called statistical significance. And I'm going a little bit fast here. It's because we're trying to just give you a summary in just one lecture hour, but you could spend a whole lecture hour only discussing statistical significance, or multiple lecture hours discussing just statistical significance. There are many, many research papers just on this topic of statistical significance, and it's always being discussed and debated and so on. So it's a big topic. So in this scenario, we have two groups of data, right? So, and we have some questions. Is the mean of group A different to, or perhaps greater than, group B? And is this likely to be a coincidence, or is it something that we can be confident that it's true? We can define two situations. This is you'll hear this term being used, this phrase being used very often. We start out with the default null hypothesis. Right? You'll hear this phrase a lot in statistics. There is no difference between the two means, or the two averages. So we have an average for one group, and we have an average for another group. And is it statistically significant? The null hypothesis states that no, there is no difference, no significant difference between the two means. That's called the null hypothesis. And then the other hypothesis is, yes, there is a difference and it's meaningful. Right, that's not called the null hypothesis, but this phrase, the null hypothesis, appears over and over again every time you test for statistical significance. Right, you'll hear the phrase, the null hypothesis. We can test, is the mean of group A significantly bigger than group B, or is group A significantly more varied than group B, right? Those are also possible hypotheses we can test, but we won't go into those today. So a very common example is the so-called Ttest. This is testing to see if there's a statistically significant difference between two groups or two data sets. So the Ttest is a hypothesis testing method for deciding whether there is a significant difference between the means of two groups, the averages. So if we apply the null hypothesis in this case, the null hypothesis is the means of the two groups A and B are the same. The non-null hypothesis is the means of the two groups are different and one is bigger or smaller than the other, right? One is, if we say the means of the two groups are different, we're conducting a two-tailed test, or that one is bigger than the other is a so-called one-tailed test. And which kind of test is appropriate depends on the question. Usually, by default, we compute this, or we use the so-called two-tailed test, right? The means of the two groups are different in a significant way. That's, by default, that's the hypothesis that we test, right? As opposed to one side or the other. So for example, is there a significant difference between heights of two different species of penguin? We're not making any assumption about whether one species is taller, right? So this is a so-called two-tailed test. And does drug B improve the recovery time from disease compared to drug A? We're only interested in this asymmetric case where recovery time is less for one group. So a one-tailed Ttest is what we could apply in that case. Now, what am I talking about? I'm talking about this value. This is the so-called Ttest, right? That's how you could, it's a statistic, right? A variance. So what do these symbols mean? This is the absolute value of the mean of the first sample, right? This is the mean of the second data set, or the second group. So you're subtracting one from the other, right? The first mean, the second mean from the first mean. This is the standard deviation of the first group, squared, then we square that. This is the standard deviation, one standard deviation of the second data set, or the second group, squared. Then we divide that by the number of samples in the first group. And likewise, we divide this by the number of data samples in the second group. We add those two together, so that's actually a distance. If you look at this, this is actually a distance. Anybody know the Pythagorean theorem? You know that that's a distance, right? We add these two together. Firstly, they're squared, then they're divided, they're added, and then we take the square root. That's a distance. So we subtract the two means from each other, and then we divide by the distance, a distance, and we get the so-called Ttest number. Now, I'm explaining that using words. It's hard to follow. It's hard to make sense of. So that's why I put a YouTube link in there. Because the YouTube video uses nice pictures, and, and they provide an example, and they're drawing out the different aspects. It's better than what I'm explaining. Of course, they've put in a lot of effort into their explanation. It's really well done. And they also show how to compute the t-test using Excel. So they take 2 data sets, and they first compute the mean of both data sets, then they compute the standard deviation of both data sets. Of course, they count the number of samples in both data sets, and then they actually compute the t-value, the t-test value. All done in Excel in that example. Gesundheit. So that's what statistics are. They're formulas, right? They're summaries and they're formulas. And then once you have this value, you have to compare it to a so-called critical value. So we compare the t-value to a critical value based on the number of samples. And how do we do that? We use a table lookup, a t-table lookup can be to look up the value c and see how statistically significant it is. How much confidence, it's a measure of how confident we are that the two means are statistically different. Right? We're testing the hypothesis, like these two averages are different, and they're different in a meaningful way. So that's what we're testing for. So if t is greater than c, we can reject the null hypothesis. If t is less than or equal to c, then we fail to reject the null hypothesis. In other words, we haven't drawn a meaningful conclusion, any meaningful conclusion based on our t-test. Imagine taking a whole course of statistics. Has anybody ever taken a whole course of statistics before? You have? I have never taken a whole course of statistics, actually. I would like to. But I haven't. I have never taken a full-length course. But some of you might be doing this in your dissertation. You know, you might have a project and you might compare 2 groups, and then your supervisor might say, okay, I want you to find out if your results, your comparisons between these 2 groups are statistically significant. Right? And then you can refer back to this lecture. Right, here's an example of penguins' flipper lengths, right? And they're divided into 3 different groups, or 3 different species. And if we look at the data, if we visualize the data, this is a histogram, right, of the lengths of the flippers. If we just look at it, it looks like there are 3 groups there, doesn't it? And we can probably draw a safe conclusion that the average of this group is significantly different than this group. But we can also measure that statistically. Yeah. And this is how we would do it in Python, right? So there's our group 1, there's our group 2. There are the 2 means, and then there's the standard deviation, right? And then there's the t-test. And then there's the t-test value and the so-called p-value. Has anybody heard of the p-value before? So our favorite statistical tests. Anybody want to take a guess as to if this is statistically significant or not? That's a difficult question. For this value, you'd have to look it up in the t-table. I mentioned that t-table. I should have a slide with that actual t-table in it. I didn't do that. But it's a table that you actually use and you look through. The p-value is kind of high here, actually. So it's not statistically very significant in this case. If you want to look more into this particular example, there's a link there. The t-test assumes that the data is normally distributed. That means there's a hill or a Gaussian distribution with only one peak. And there are other kinds of tests, so-called non-parametric tests, that can be used if the data is not normally distributed, right? And here are some examples of different variations, right, of distributions. Okay, the problem with the t-test, or one of the aspects of the t-test that you might have noticed, is you're generating the so-called t-value, but then you have to compare it to a so-called critical value. So there's always this comparison going on. The p-value attempts to abstract that comparison away. So you don't need a special table when you derive a p-value. You don't need a special table to say whether or not it's significant anymore. So we can convert the t-value into a p-value so that it's on a probability scale rather than based on some critical threshold value. Right, and the typical value is 5% or 0.05. If we get a p-value of less than 0.05, we can be confident that we can reject the null hypothesis. I'm using the lingo of the statisticians there. We reject the null hypothesis if the p-value is less than 5%. So here, if I go back a slide, that p-value is greater than 5% here, just in case you're interested. And again, this is a big topic. Like, we could do a special lecture just on p-values, right? So it's a very popular topic. And I encourage you to do a little bit of outside reading and supplement what we have here with some outside reading, or maybe some outside tutorials that I've put in the lecture slides. And by the way, we're going to point out one of the weaknesses of p-values, another weakness right now, and this is another reason why visualization is good. It is possible to perform many experiments, right, and then only report on the experiments that have a low p-value, result in a low p-value, and then leave out everything else. So I studied physics when I was a student, undergrad student, and one of my professors said in the experimental physics class, he said, in physics we conduct an experiment 1,000 times. So we conduct an experiment 999 times and we fail, and then on the 1,000th time we succeed, and we only report the one success and we leave out the other 999 failures. This happens, this is a common phenomenon, right? And in this scenario, why do I bring up this? That's what I'm actually talking about here, is you can conduct many experiments, generate poor p-values, and then only report positive ones, right? And in the statistical, this can be called p-hacking. I don't know, whatever, that term is not very, or data dredging. In other words, we can generate artificial connections between data sets that don't really exist in reality. But we can apply other statistical methods like Bonferroni correction that can be used to look for those suspicious cases. And I'm just going to wrap up here. This is an example, right, of trying to draw a relationship between two data sets that doesn't really exist, right? Per capita cheese consumption versus the number of people who died by becoming tangled in their bed sheets. Right, there's no relationship there, but if we conduct enough experiments and run enough p-values, we can try to create an artificial relationship there. And there are some more. Total revenue generated by arcades versus the computer science doctorates awarded in the US. It looks like there's a relationship there, but it is not. And there's another example. Okay, any questions? That was a very fast introduction to quantitative methods. When it comes time to do your dissertation, if you need to apply these quantitative methods, your supervisor will ask you to do so, and then you'll have to figure it out. But this should help. And I've put a YouTube channel there that's very helpful for statistical methods. There are 2 YouTube links in there that both point to channels, very good statistical YouTube channels, that actually they do a better job than I do, actually, of introducing these statistical measures. So it's almost more important to know where to look, how to do these things, than to know how to do them right now, if you know what I mean. Any questions before we wrap up? Okay, thank you all. You're free. Have a good Wednesday.